Let's look now at section 10.3. Let's talk about the calculus of parametric equations. Now, in a previous section, we defined parametric equations, and those are going to be two equations for x and y for the coordinates of a point in space that are given by as a function of a third parameter. Your plane curve is given by the parametric equations x equals to f of t and y equals to another function, let's say g of t. Okay. All right, now we can define a curve on a plane using these equations. But one of the things that we've seen over and over again in this course, in Cal 1 as well, is anytime you define a curve, well, we can define the derivative, the antiderivative. We can talk about arc length and inflections and concavity and all the other things that are inherent to the study of calculus. So if this is a curve, well, then how do I talk about it? If I have some parametric curve, how do I find the equation of a tangent line? After all, this is a circle, and as we've seen before, circles can be parameterized using sine and cosine. Namely, okay, I give you an angle theta. The x value here is given by the cosine of that angle theta, and the y value is given by the sine of that angle theta. Well, how do I find the equation of this tangent line right here? I say, well, okay, well, first let's start off by finding the slope of the tangent line. And that requires us to take a derivative. Okay, but then the question stands, how do I find the derivative of a curve that's been defined parametrically? Well, it turns out it's not very difficult at all. This section opens with a theorem which states the following. Let's start off with a smooth curve. Let C be a smooth curve on the plane. When we say a smooth curve, we mean something that doesn't have any cusps or something that doesn't have any breaks in it, something that's continuous and it has a continuous first derivative. Right? So let C be a smooth curve on the plane that has been given by the parametric equations x equals to f of t and y equals to g of t. It's given by that kind of parametric equation. Then this derivative, then let's see here. The slope of the line that is tangent to C at a point x comma y is given by the traditional notation dy dx, which is going to be given by dy dt divided by dx dt, provided that that denominator is not equal to 0. Well, what is this saying? What it's saying is, if you want to define a derivative on a parametric on a curve that's defined by parametric equations, the way you do it is by saying, okay, what is the derivative of y, not with respect to x, but with respect to t? Separately, what is the derivative of x with respect to t? And then you divide those. Right? This is the derivative notation. This is Leibniz notation. This is Leibniz notation. This is Leibniz notation. This is just regular old division. The proof of this is about as straightforward of a proof as one could want for something that looks somewhat complicated. Let's begin with a small change in our differential of our parameter. So let's begin with a small little change in t which we call delta t. Let delta t be some number that's greater than 0, and again, it represents a small change in t. Well, if that's the case, then a small change in y, well, notice y is given by g of t. So if I want a little change in y, it's going to require a little change in g. Okay, so that'll be g of t plus delta t minus g of t. Okay, so this is where y is. If I want a little change in y, that means I need to find the difference between this and some other point that's very nearby. Okay, so here's this. Here's another point that's very nearby, and I want to find the difference of those two. And the same thing would be true for x. So delta x is given by, instead of g, we're using f. So that's going to be f of t plus delta t minus f of t, like that, for the exact same reasons. Okay. Well, now, if I want to find the derivative of y with respect to t, I know that's got to equal to the limit as delta x approaches 0 of delta y over delta x. Right? Well, yeah, but those can be replaced by those. So that's going to be the limit as this, which is my delta y, over this. And now here, well, I want my delta x to approach 0. Well, yeah, but delta x is going to approach 0 when delta t approaches 0, right? If this was 0, f of t minus f of t would be 0. That's what I want. I want delta t to go to 0. So that's going to happen if delta t is allowed to get very, very small. So here, dy dx is equal to this, which is the same as this. All right. Try to finish this yourself. Ask yourself, those numerators and denominators, do they look, as approaches 0, do these look like anything familiar? Go ahead and pause the video and see if you can finish the proof yourself. Once you get somewhere conclusive, go ahead and unpause the video and we'll finish it off ourselves. We'll finish it off together. So this almost looks like a derivative. If I didn't have that there, limit as delta t approaches 0 of g of t plus delta t minus g of t, that's almost the derivative of g. Oh, but the denominator's wrong. Here I shouldn't have that thing. I should just have delta t in my denominator. Oh, okay, so let's give it delta t. Since this is true, we can say that dy dx is given by the limit as delta t approaches 0 of g of t plus delta t minus g of t over delta t. Like that. But whatever I do to the numerator, I have to do to the denominator. So that would make my denominator also over delta t. So that's going to be f of t plus delta t minus f of t, like this. But now, given properties of the limit that we learned in Cal 1, if I take the limit of a quotient, that's the same as taking the limit of the numerator over the limit of the denominator. So I'm taking the limit of this numerator divided by the limit of this denominator. But now that's the derivative of g with respect to, well, normally this would be x and delta x, but this is t and delta t. Okay, so it's the limit of g with respect to not x, but t. So this would be the derivative of g with respect to t over, this is the derivative of f with respect to t. So that's df dt. Oh yeah, but g, if you go back up here, g is the function that gives you y. And here f is the function that gives you x. So in other words, f is just a different label for x, and g is just a different label for y. So if I say I want the derivative of g with respect to t, that's just the derivative of y with respect to t, over the derivative of f with respect to t is really just dx dt. Oh, but that's what we were trying to prove. And that concludes our proof. All right. So let's take a look at some examples of how we use this. So let's consider the example where we want to find the equations of the tangent lines that's bad grammar. Find the equations of the lines tangent to the curve that's given by x equals t squared minus t, and y is given by t to the third minus 3t minus 1, where the curve crosses itself. Okay. Visually, what we have is this graph here. If you were to graph that set of parametric equations, you notice you have a graph that eventually crosses through itself. So that's the first thing we want to find. We want to find where does this cross. Now, from the graph here, it looks like it's going to cross 2 comma something. But again, we need to be certain as to where it crosses. Plus, you may not always have the graph. Creating a graph can sometimes be time-consuming. So here, let's take a look at a way of finding where it crosses without having to actually go through and form a complete graph. So the first part of this problem isn't calculus, it's just algebra. We want to find where does this thing cross itself. Okay, so part 1, where does the graph cross itself? When we say a parametric equation, a parametric set of equations are going to give you a graph that crosses itself, really what we're saying is you're going to have one value of t and then another value of t, which will give you the same x and the same y. So maybe t is equal to 5 will give you 1 comma 3, and t is equal to 50 will give you 1 comma 3. That's all we're looking for. We're trying to see what values, different values of t, give you the same x and y. So here we're going to say, okay, let's pick 2 values of t and plug them in. And you say, we're going to pick numbers and plug them in? No, we're doing this algebraically. So we're going to pick arbitrary values. So here we're going to say, all right, let t be 2 different values, A and B. So what we want is we're going to form a system of equations. We say, okay, that whatever A and B that we choose, in the end, if you plug in A or if you plug in B, you should get the same answer. So here, A squared minus A will give you an x value. B squared minus B will give you an x value. And we want to find the place where those x values are the same. We want to find the 2 A, B value. We want to find the 2 parameters that if you plug in one number and if you plug in a completely different number, you still get the same x value. And likewise, you want to plug in one value that'll give you a y. And we're plugging in A. Now I want to pick a different value and plug that in too. So b to the third minus 3b minus 1. But even though this a and this b are different, if the graph is going to cross itself, that even though a and b are different, they should still give you the same y value. Just like that. So what we have is a system of equations that we need to solve. And here, this system of equations, first of all, let's simplify things ever so slightly. You will notice that the second one, we can just add 1 to both sides and get rid of a constant. The smaller the system equations are, the better off we'll be. Okay, just like that. So now what I want to do is I want to say, well, look, if I take this equation on the left side, we can move things around just a bit. Here, let me put all my squares together. So let me subtract b squared from both sides. And let me add a to both sides. And that'll give me a squared minus b squared is equal to a minus b. Notice that a squared minus b squared can be factored as a plus b times a minus b. So now a plus b times a minus b is equal to a minus b. Notice these are the same. So I'm going to multiply something times a plus b and not have it change. Well, that must mean a plus b is equal to 1. Right? 1 times something is itself. If this wasn't 1, this would have changed. But it didn't change, so it must be the number 1. Okay? So here, that allows me to isolate. I can go ahead and subtract the b over to the other side, and it'll give me 1 minus a is equal to b. Okay? So now I can take this and plug it in over here. And even though I could plug it in right here the way it currently is, you'll notice that that's a cubic equation, and cubic equations might be a little difficult to handle. So we can plug it in now, but you'll find it's a little easier if you do something similar to what we had before. Here, let me go ahead and subtract b to the third and subtract b to the third, and that's gone. And let me add a to the third and add, not a to the third, 3a, and that's gone. And now that's going to be a to the third minus b to the third, which is equal to 3a minus 3b. But again, that can be factored, and some stuff will divide away here as well. This is the difference of cubes, which factors as a minus b times a squared plus ab plus b squared. Here, this side factors as 3 times a minus b. And here, these a minus b's are exactly the same, which means this item in parentheses must be the same as this number 3. So here this gives you a squared plus ab plus b squared is equal to 3. And now we have a quadratic, which is much smaller than a cubic, so now we can go ahead and plug in there. If you want, you can always plug the b equals 1 minus a up here at the beginning, but that's going to be a lot more work, whereas here, one extra step brings down the power and requires a lot less work now. So now this can be written as a squared plus a times b plus b squared is equal to 3. And now my b's are going to be replaced by 1 minus a. And now I'm left with a quadratic equation, which is reasonably nice to solve. I have a squared plus a minus a squared plus, if I square all this stuff, I'm going to get 1 minus 2a plus a squared is equal to 3. I can go ahead and combine some like terms. Notice a squared minus a squared are gone. And I'm left with that a squared. I have minus 2a plus a is just minus a. And then I have a plus 1 right here is equal to a plus 3. If I subtract the 3 over this way, this is now a nice, simple to factor quadratic equation. If you want to use the quadratic formula, that's fine, but that's kind of overkill for this problem. Because after all, this one factors as a minus 2 and a plus 1 is equal to 0, which means that a must equal to positive 2 or a must equal to negative 1. And there we go. We don't actually have to go through and create the graphs. We found exactly here are the two different parameters that are going to give me the same point. So here, let's see what point that is. If I say, okay, so remember, these are just two different parameters, two different values of t, which are going to give us the same point. So here, if I have t, I have x, and I have y. Let's see what happens. Let's confirm that I've done this correctly. If a is equal to 2, well, that's a parameter. Right? These are my parameters. So if t is equal to 2, let's go back to our original definition. T squared, well, that would be 2 squared is 4. 4 minus 2 is 2. On the other hand, if I plug in 2 here, 2 to the third is 8. 2 times 3 is 6. So 8 minus 6, that'll give me 2, minus 1 gives me just 1. Okay. On the other hand, what if I plug in a equals to minus 1? Okay, well, let's see. That'll be negative 1 squared is positive 1, and then minus a negative 1. So 1 minus a minus 1, that's the same as 1 plus 1. That's 2. And if I plug in negative 1 right here, negative 1 to the third is negative 1 minus negative 3. Okay, so that's negative 1 plus 3. That's 2. 2 minus 1 is 1. And sure enough, even though I had two different parameters, I still get the same point, 2 comma 1. So here, where does the graph cross itself? It crosses itself at 2 comma 1 when t is equal to 2 and t is equal to minus 1. Okay? Notice there was no calculus in that problem. That was strictly algebraic. We were just trying to find where does that graph cross itself. Now, let's actually take a look at finding where, what are the lines of tangency to the curve. And once we have this, the rest of it is reasonably nice. Because now all we need to do is we need to use our theorem to find the derivative of our function at those points. Note that our theorem simply says to find dy dx, we're going to find dy dt, we're going to find dx dt, and we're going to divide. All right. So part 2 is now let's go ahead and find the tangent lines. Okay. Let's find our derivatives. I know that x was given by, what was my equation? X is given by t squared minus t. And y is given by t to the third minus 3t minus 1. Okay. Here I can find the derivative of x with respect to t, dx dt. And that would just be, well, just a regular derivative. That would be 2t minus 1. Okay. Taking the derivative with respect to t of this one, well, again, that's just a normal derivative with respect to t, though, instead of with respect to x as usual. But it follows all the same rules. That's going to be 3t squared. That's going to be minus 3t. And the derivative of a constant would be 0 regardless of what variable we're using. Okay, so there are dy dt and dx dt. So by our theorem, dy dx is going to equal to dy dt over dx dt, which is going to be 3t squared minus 3 over 2t minus 1. And that's it. There's your derivative. So now we just need to find the slopes of our tangent lines. Well, we have the derivative. And just like in Cal 1, to find the slope of a tangent line, we simply take the derivative and evaluate it at the point that we care about. But notice that for this problem, we had two different values. Here we said, okay, our graph's going to cross at 2 comma 1, and that's going to happen when t is equal to 2 and when t is equal to minus 1. So here we're going to find two different tangent lines. Okay, but they'll have slopes given by this equation. When t is equal to 2, the slope of the tangent line is, we're just going to take this and plug in 2. So that'll be 3 times 2 squared minus 3 over 2 times 2 minus 1, which will give us 4 times 3 is 12, minus 3 is 9, over 2 times 2 is 4, minus 1 is 3. Oh, and there we go. There's the slope of our tangent line. So I now have a tangent line. I now have a tangent lines. I have its slope. Okay, well now I have a slope. And I have a point. Because after all, we know that when t is equal to 2, we found that the point of intersection was 2 comma 1. Okay, so we have a point and we have a slope, which means now we can find an equation. Because after all, we just want y equals mx plus b. That's the equation of a line. But now we know our m, and here that's an x and a y value. So here this gives us 1, that's our y value, equals m, which we just found, times x, again, that's our x value, plus b. So this gives us 1 equals 6 plus b, and therefore b must equal to negative 5. And so that gives us everything we need. We have our slope, we have our value of b, we have something that can give us a y-intercept. So that means that the tangent line will be y equals, we have our slope, 3x, and we have our b, minus 5. And that's the equation of one of the tangent lines. We still have a second tangent line. We have the tangent line for whenever t is equal to negative 1. We're still missing that one. So go ahead and give that a try. See if you can find the second one. Pause the video and use the information that we have so far to find the equation of the missing tangent line. When you're done, unpause the video and we'll go through it together. All right, so let's take a look. We already did this when t is equal to 2. So now let's find it when t is equal to minus 1. All right, when t is equal to minus 1, the slope of the tangent line is, well, here's the derivative with respect to t. So we're just going to find it at this value. So that'll be 3 times negative 1 squared minus 3 over 2 times negative 1 minus 1. And that'll give us positive 1 times 3. Oh yeah, but now 3 minus 3 is 0. And over here, that's going to be negative 2 minus 1 is negative 3. And here, that's 0. So here, this is a special case. The slope of the tangent line is 0, which means it's going to be a horizontal line. Well, thinking back to our algebra, horizontal lines have the equation y equals to something. Y equals to, well, we happen to be at the point 2, 1. So if I have a horizontal line, I know I have to have y equals something, and I know given the point that I am passing through, it has to be y equals to 1. So this one is a little bit less work because you don't have to worry about finding the value of b. Since the slope is 0, this y value here is your intercept point there. And that gives us both of our tangent lines. And as a quick visual, that's what it would look like. Here's our curve. Here's its point of intersection. It turns out to be 2, 1. And here you see that if you're following the curve along this path, along this lower arc, the tangent line is this flat line, which is y equals to 1. But if you loop around, come back down, and then start to come back up, when you cross through the point again, it'll have a different tangent line. This time it'll be this red line, which was y equals 3x minus 5. All right? So it'll have one tangent line on its first pass, and then it'll have a second tangent line on its second pass, just like that. Now, once we've defined the first derivative, defining higher order derivatives is simple enough. You simply take the derivative you have and take another derivative. We can define the second derivative, third derivative, fourth derivative, and so forth, as long as we know how to define one. But you do have to be slightly careful because there is a common mistake that people will make when doing this. So here, instead of trying to go through the different scenarios, let's just go through an example and see the correct way to do this. All right? Let's consider a set of parametric equations, and let's go with x equals to t squared plus 5t plus 4. And let's take y to be given by 4t. And the question is to find both the slope of the tangent line. So here they don't need the full equation, just the slope. But the other question is to find the concavity, which, if you remember from Cal 1, involves the second derivative. So it says find the slope of the tangent line. And here there will only be one for this example. And concavity of this curve at t equals to 0. Okay, so just like in Cal 1, we're going to need the first derivative to find the slope of the tangent line, and we're going to need the second derivative to find the concavity. All right, so here we go. We know that dy dx, given our theorem, is dy dt over dx dt. So we just need to find those. Here, dy dt is going to be the derivative of 4t with respect to t, or in other words, it's just the number 4. Dx dt is going to be the derivative of t squared plus 5t plus 4 with respect to t, which is just 2t plus 5. Like that. And now we want to find what happens at t equals to 0. So, at t equals to 0, the slope of the tangent line is going to be given by 4 over 2 times 0 plus 5, which is just 4/5. All right, and there we go. There's the slope of your tangent line. Now, to find the concavity, we're going to find the second derivative. Note how we're going to find the second derivative. To find the second derivative, and we're going to use the same notation that we have in previous courses, we're going to write this as d squared y dx squared. We're going to take the derivative of the derivative. Okay, that seems simple enough. We're going to take the derivative with respect to t of this result. So that's d dt of dy dt over dx dt. But notice that that needs to be divided by dx dt. And you say, why? Because that's how we take a derivative. If this is your function, you're going to take its derivative, but then you're going to divide by the derivative of the x variable with respect to t. We're essentially mirroring this. Here's your function, here's its derivative, and then divide by dx dt. All right, well now here's your function. Okay, take its derivative, and now divide by the derivative dx dt. That's something people will often forget. They'll remember take the derivative of the derivative, and they'll forget that there's an extra expression down here. So let's see what that's going to look like. If I'm going to take dy dt dx dt, well, that's this expression that I just found. So what I'm going to do is I'm going to take the derivative with respect to t of 4 over 2t plus 5, but then I need to divide that by dx dt. You say, well, we had dx dt up here. Well, it's the same one. We're going to divide that answer by 2t plus 5. If we were to take a third derivative, we would do the same thing. We would take the derivative of this answer and then divide by dx dt. Every time you're going to take a higher order derivative, you're going to take the derivative of the answer before it and then divide by dx dt. So here, let's go through and do the computation. Here, that's going to be, let's see. We would have to, well, let's see. That would be 4 times 2t plus 5 to the minus first power. So here, let me rewrite this way. I'm going to take d dt of 4, and instead of dividing by this, I'll say times 2t plus 5 to the minus first power. And again, I'm dividing by 2t plus 5. To take the derivative here, that's just the power rule. Take your minus 1, bring it down. Subtract 1 from the power. But now, don't forget the chain rule. This was a composition. This was a smaller function inside of a larger function. So here we're going to multiply by the derivative of the inner part, which is the number 2. All right, there's our derivative. And all of that is over 2t plus 5. We can now write that as minus 4 times 2. We can write that as minus 8 over 2t plus 5 squared. All right, that's your 8. This has got a negative power, so it brings it down to the denominator. And now that is over 2t plus 5. Oh, but now negative 8 over 2t plus 5 squared divided by another 2t plus 5. We can simply merge those denominators to give us negative 8 over 2t plus 5 to the third. And that is our second derivative. Notice you take the derivative of the first derivative, but once you finish doing that, you're going to divide that answer by dx dt again. If we're going to take a third derivative, you would take the derivative of this and then divide by 2t plus 5 again. Every time you take another derivative, you're dividing by 2x plus t, dx dt, I mean. So now, there is our result. And now we need to find the concavity. So just plug in 0 and see what happens. So at t equal to 0, we get negative 8 over 2 times 0 plus 5 to the third, which is negative 8 over 5 to the third, since that's 0. And 5 to the third is 125. Not that that number really matters, because all that really matters is that that second derivative is negative. And since the second derivative is negative, that means your function is concave down. So at t equals to 0, the curve is concave down. And that makes us happy. Here, go ahead and give this a try. Just find dy dt, dy dx and d squared y dx squared. So just find the first derivative and second derivative. From there, you could find the slope of the tangent line. You could find the tangent line. You could find the concavity. You could find the inflection points. You could find lots of things. But basically, it boils down to, can you find these derivatives first? So find those for the curve given by x is equal to theta minus the sine of theta for x, and for y, we're going to use 1 minus the cosine of theta. So go ahead and pause the video, give this a try, and once you have an answer, go ahead and unpause, and we'll go through it together. All right, so let's take a look here. We're going to start off by finding the first derivative, and that's dy dx equals dy dt over dx dt. Okay. The derivative of y with, I guess that should be theta since we're using a different variable here. So the derivative of y with respect to theta, well, the derivative of 1 is 0, and the derivative of minus cosine of theta would be sine of theta. Okay. Now we're going to divide that by the derivative of x with respect to theta. Well, let's see. The derivative of theta with respect to theta is 1. The derivative of sine of theta is, with respect to theta, is cosine of theta. And don't forget, you have a minus right there. All right, and there we go. By our derivative, the derivative dy dx is equal to sine of theta over 1 minus cosine of theta. So now, to find our second derivative, to find d squared y dx squared, we need to take the derivative with respect to theta of our current derivative, sine of theta over 1 minus the cosine of theta, and then that's going to be divided by dx d theta, or in other words, 1 minus the cosine of theta. Just like that. Here, it looks like we want to use the quotient rule to take the derivative. So that's going to be the bottom times the derivative of the top, which is just the cosine of theta, minus the top times the derivative of the bottom with respect to theta. The derivative of 1 is just going to be 0, and the derivative of negative cosine of theta is just going to be sine of theta. All over the square of the denominator. 1 minus cosine of theta quantity squared. And all of that will be 1 over 1 minus cosine of theta. Okay. Let's see here. Here, these two denominators can just be merged now. So we can write this as 1 minus the cosine of theta times the cosine of theta minus the sine of theta times the sine of theta divided by 1 minus cosine of theta squared times another 1 minus cosine of theta is 1 minus cosine of theta quantity cubed. Well, that numerator can be simplified quite a bit here. I can distribute that cosine of theta to give me 1 minus, oh, not 1 minus, it'll give me cosine of theta, right here, cosine of theta, minus cosine squared of theta, minus sine squared of theta, over 1 minus cosine of theta quantity cubed. But notice now, sine squared of theta plus cosine squared of theta would equal to 1. Oh, but now both of these are minus. Okay, so all of this right here, by the Pythagorean identity, is just minus 1. So here we can write this as cosine of theta minus 1. This becomes minus 1 over 1 minus the cosine of theta quantity cubed. Notice that that almost divides out. Oh, but those are in the wrong order. Okay, so factor out a negative. Here, if we write this as negative 1 minus the cosine of theta. All right, notice that's still minus 1 like it was up here. And double negative will still make that a positive cosine of theta like it was up here. But now by writing it this way, we note that we have one of our 3 factors in the denominator will divide out by one of these. And so in the end we get minus 1. This divides with one of these. And this gives us minus 1 over 1 minus the cosine of theta quantity squared. And that is our second derivative. Whereas that was our first derivative. The last thing we want to look at in this section, let's take a look at the concept of arc length, which is something we've seen before, but now in the context of a set of parametric equations, you'll notice that there's a minor difference in our computation. It's not a difference in the meaning, it's just a difference in the computation. You'll think back to Cal 1, where you first learn about arc length, which says, okay, I have a curve that is, well, it's curved. It's bent. Well, I want to find out how long it is. Well, what I want to do is I want to go ahead and straighten it out, make it nice and flat, and that way that's something I can measure. You say, well, how do you do that? Well, you can't perfectly make it straight, but we can approximate it. Whatever our curve is, we can say, okay, part of it's flat, and then another part of it's flat, and another part of it's flat. And if we get enough small flat pieces, that approximates our curve about as well as a perfectly straight line would. And from that, you got the result that the arc length of a curve is equal to the integral from a to b, from its beginning to its end, of the square root of 1 plus let's use h here because I've been using f and g as my parameters. So let's say h prime of x quantity squared dx. And this is the result that we saw in Cal 1. This is the arc length of a curve given by the function f, I guess h in this case, over the interval from a to b. Okay? So you have a curve. It begins where x is equal to a. It ends where x is equal to b. And I have some function that gives me that curve. Okay? Well, now we have an alternate way of expressing a curve. So here we can say, okay, well, look, the arc length can be given this way. It's the integral from a to b of the square root of 1 plus dy dx quantity squared dx. And you say, well, that's the same thing. You're just using Leibniz notation as opposed to the Newtonian notation. Right? It means the same thing. Dy dx is the same as the function prime. Well, sure. It's absolutely true. But if you write it this way, we can now use our previous theorem, which says that, hey, if I want to find dy dx, that's easy to do if I have x and y written with parametric equations. So here, I can write this as the integral from a to b of the square root of 1 plus dy dx can be written as dy dt over dx dt, quantity squared. Just like that. Well, that can be written, after all, this is a fraction. This literally is just one derivative divided by another derivative. So if I square it, I can just square the top and bottom separately. So I can write this as the integral from a to b of the square root of 1 plus dy dt squared. It's the square of that derivative over dx dt squared dx, like that. Well, now here I can give these a common denominator. I can write this as the integral from a to b of the square root of dx dt squared over dx dt squared. That's the same as the number 1. But by writing it this way, I now give them a common denominator. But because they have a common denominator, I could always merge those together. So I can write this as the integral from a to b of the square root of dx dt squared plus dy dt squared over dx dt squared dx. But I can write this as two separate radicals. I can write this as the square root of that top over the square root of the bottom. Oh, but now, I forgot my square there. Oh, but now I have the square of a square root. So this is the integral of the square root of dx dt squared plus dy dt squared from a to b. Here I have dx divided by dx dt, which is just going to give us dt. But notice, dx dt, that's just the derivative of the function that gives you x. It's the derivative of one of your two parameters. Likewise, dy dt is just the derivative of your other function, the one that gives you the y coordinate of your parameterization. So here you can write this as the integral from a to b of the square root of f prime of t, quantity squared, plus g prime of t, quantity squared, dt. So let's take a look at an example of how to use this. Note, this is the same arc length formula that we've had since Cal 1. The difference isn't what we're doing, it's the representation. Here we're no longer thinking of y as a function of x, we're thinking of both x and y as functions of a third variable, a parameter. So even though the meaning hasn't changed, you'll notice that some of our computations will look a little different. And a lot of them will look a little bit simpler. So let's take an example. So let's consider the example where let's find the arc length of the curve given by the parameterization x equals the arc sine of our parameter t, and y is going to be given by the natural log of the square root of 1 minus t squared. And here we're going to find the arc length over the region, over the interval where t goes from 0 to a half. For t that's in the interval from 0 to a half. Okay, just like that. All right, given our result that we saw just a moment ago, we're basically just going to take the derivatives of each of those. You're going to square them, add them together, put them under a square root, and then take an integral. All right, so let's do that. First of all, let's find these derivatives. Let's find my dx dt. The derivative of the arc sine of t, that's just going to be 1 over the square root of 1 minus t squared. dy dt, well, that's going to be the derivative of this one here. You might have an easier time if you write this in its alternate form. Remember, one of the nice properties of a natural log is you can take a 1/2 power. After all, that's a 1/2 power. You can pop it to the outside. So you will probably find it easier to think of y as being 1/2 the natural log of 1 minus t squared. Just like that. You can think of it with the square root, but that'll make the derivation just ever so slightly longer and messier. This way it's a lot nicer, because here all you do is you say, okay, that's going to be 1/2. The derivative of the natural log of something is, the derivative of the natural log of something is going to be 1 over that something times the derivative of that something, which in this case is just negative 2t. And so here these 2's cancel out, and we're left with negative t in my numerator over 1 minus t squared in my denominator. Okay, well, now it's not enough to take those derivatives. I have to take those derivatives and square them. All right, well, now let's square everything. We're going to take dx dt and then we're going to square it, which is the same as 1 over 1 minus t squared square root squared. Here we're squaring both sides. And so here that's just going to give us, squaring 1 gives us 1, and squaring that square root gets rid of the square root and just leaves us the stuff inside. So 1 over 1 minus t squared. Now if I wanted to take dy dt and square it, well, that's going to be the square of negative t over 1 minus t squared. Negative t times negative t is positive t squared. And here 1 minus t squared squared. Okay. So now, to set up my integral, I'm going to take those two things that I just found, add them together under a square root. So the arc length is going to be, we're going to take these two things that we just found, 1 over 1 minus t squared, and add that to t squared over 1 minus t squared squared. We're going to stick that under a square root and then integrate from the beginning of our interval, which is 0, to the end of our interval, which is a half, with respect to t. Okay? And that's our setup. That's how you find the arc length. You're going to take your x, your y, you're going to derive each of them, you're going to square each of them, and then those results get added under a square root. Now integrate from 0 to 1/2, or whatever your boundary is there. Right? So here, we now need to integrate. This one it does take a bit of effort, but thankfully this comes at chapter 10, which means we've had a whole 4 chapters of lots and lots of integration. Right? So here I'm going to go ahead and pause the video and use this as a review. Go ahead and look over what we've done here, but also use this as a review, see if you can integrate this expression. All right. Once you're done and you have an answer, go ahead and unpause the video and we'll finish it off together. All right, so here, it'll be nice if I give these a common denominator. So I can write this as the integral from 0 to a half of the square root of, here, these almost have the same denominator. This just needs another copy of 1 minus t squared. So I can write this as 1 minus t squared over 1 minus t squared times 1 minus t squared plus t squared over 1 minus t squared squared dt. Here all I've done is I've given these, I've multiplied top and bottom by 1 minus t squared. All right. If these two cancel out, I would get this. But if I don't let them cancel out, notice I now have a common denominator, which means I can now write this as integral from 0 to a half of the square root of, well, notice now t squared and negative t squared go away. So that'll leave me the numerator 1 over 1 minus t squared squared dt. And of course here I can take the square root of everything. So that's the integral from 0 to a half of, the square root of 1 is just going to be 1. And the square root of 1 minus t squared squared is just 1 minus t squared with respect to t. All right. At this point, we have a few different ways we might go about it, but I think the simplest way will just be to separate it. We can write this using partial fractions. Here, this is going to be the integral from 0 to a half of something over 1 minus t plus something over 1 plus t dt. Yeah? If you multiply these together, that's going to be 1. That would be minus t plus t would cancel out, and then minus t squared. So that is the correct factorization of my denominator. Here I just need to find what those numerators are. Let's do a quick partial fraction decomposition down here. Here if I have 1 over 1 minus t squared is equal to a over 1 minus t plus b over 1 plus t. All right. That is got to equal to the sum of this and this with some constant numerators. I can now multiply this by 1 plus t and 1 minus t. I can multiply this by 1 plus t and 1 minus t. And I can multiply this by 1 plus t and 1 minus t. Here, I've multiplied by 1 plus t and 1 minus t all the way across. Those make that go away. These two divide away, and these two divide away. So now this is 1 equals a times 1 plus t, that's all that's left there, plus b times 1 minus t, that's all that's left there, which is the same as saying 1 is equal to a plus at plus b minus bt. Just distribute the a and distribute the b. But now we can go ahead and match these up. I notice that if I combine these two terms, I should get 0. All right, at minus bt should give me 0t because there's no t out here. So I should be able to get a minus b. If I put those together, I should get 0. If I put those together, a plus b, I should get 1. And there's my system of equations. But now if I add those two equations in that system, that's going to give me 2a. Those would give me 0, and that's equal to 1. So here I have 2a is equal to 1. And if I divide both sides by 2, that gives me a is equal to a half. But again, a minus b should equal to 0. Oh, so that means b should also equal to a half. Right? That way, 1/2 minus a half would be 0. Meanwhile, 1/2 plus 1/2 would be 1. So it turns out both of these numerators are a half. Just like that. And now we can integrate each of those as a logarithm. So here this is going to be 1/2 the natural logarithm of the absolute value of 1 minus t. Now note the chain rule here. The derivative of 1 minus t is negative 1, so we would have to have a minus 1 there. Here, that's going to be plus. Here, there's no negative in the denominators in front of the t, so that's not going to be a negative. That'll be a plus. That's going to be plus 1/2 the natural log of the absolute value of 1 plus t. And now here, we're going to evaluate from wherever t is equal to 0 up to wherever t is equal to a half. All right. If t is equal to 0, notice that none of this is anything. If t is equal to 0, 1 minus 0 is 1, and the natural log of 1 is 0. And same thing over here. 1 plus 0 is 1, and the natural log of 1 is 0. So here the 0 makes everything 0. So all that really matters is plugging in the 1/2. So this will give us negative 1/2 natural log of the absolute value of 1 minus 1/2 is 1/2. Plus 1/2 times the natural log of the absolute value of 1 plus 1/2 is 3/2. And there we go. This would be our result. Here you actually can simplify this a little bit more. Notice I have a 1/2 in common. I could factor out a 1/2. I can write this as the natural log of, here the absolute values don't matter since they're already positive numbers anyway. So I could write this as the natural log of 3/2 minus the natural log of 1/2. And then there's a property of natural logs that says if I'm subtracting two natural logarithms, I can just take the argument of the first natural logarithm and divide it by the argument of the second natural logarithm. So here this is 1/2 times the natural log of 3/2 over 1/2, and 3/2 divided by 1/2 is just 3. So here that's 1/2 the natural log of 3. And there's another property that says 1/2, if there's a constant here, it can be brought inside. So we can even write this as the natural log of 3 to the 1/2 power, or in other words, natural log of the square root of 3. So there we go. There's a bunch of different ways you can write this. Let's see here. Yeah, all of these are potential answers. All of these are good. Okay. Obviously, that's the simplest one, but there's a few other ways you can write it. And that's the arc length. That's the length of the curve given by this parameterization from 0 to 1/2. You do have to have some boundaries because otherwise, well, you wouldn't have any numbers to plug in, which means you would get a variable expression like you have here. You wouldn't get a constant like we have over here. All right? So that is it for that problem, and that is it for that section. As an assignment for this section, let's see, let's have you try, let's do this. Section 10.3, do 9 through 17 odd, and then do 27 through 53 every other odd, meaning every fourth problem, every other odd. And that should suffice. If anybody has any questions, please make a note of them, reach out to me, and I'll get back to you as I can. And I hope everyone has a nice day.